the first session. So we're pleased to have Antoine Bourget, who will tell us about S-duality.
Okay, thank you very much. Thank you for coming. Thank you for inviting me. It's great to be back in Trieste. Actually, I was there a few months ago, and I gave a talk on work with Marcus, Quentin, and Sinan here about some classification of quivers. And it would have been adapted to this conference, which has quivers in the title. But okay, I thought I should not repeat because most of you already heard that story. So I decided to talk about something else. And well, unfortunately, there will be no quivers, but hopefully symmetries and SCFTs. So what I will be talking about today is incarnation of S-duality in n = 4 super Yang-Mills from the IR. So what I mean by the IR here is the vacua of the theory. So first of all, the n = 4 preserving vacua, and also other types of vacua preserving less supersymmetry, so after mass deformation. So this is based on these two papers. Oh, maybe I should point here. So there are two papers. One of them already appeared with well, this list of authors, Jeremias, Ricardo Argyres, Valdo, and Romain. And the other one, and actually most of the talk will be based on the second one, which has not appeared yet, but I hope that talking about it here will push for the appearance of this paper, with Philip, Argyres, Julius, Matteo Lotito, and Mitch Weaver. So it will be mostly about that, but then at the end, I will try to connect to the other paper. So what do we want to do in this talk? The motivation is that well, as you know, moduli space of vacua, it's a fundamental geometric structure which is attached to any SQFT. And it contains a lot of data about the local structure of QFT. So for instance, the coordinate ring typically of a branch of vacua gives OPE of local operators, Kahler rings, and so on. But then here I want to ask, does it know about global structure, which are the additional data that you need? For instance, if you want to define your theory on a topologically non-trivial manifold, so typically it's the difference between SU2 or SO3 gauge theory. So does the moduli space of vacua know about that? And how are dualities encoded? And as you know, these two things are very related. And the toy model in which they are the most well illustrated is n = 4 super Yang-Mills. So that's what I will focus on. So the goal is really to show how global structures and dualities are encoded in the moduli space of vacua. And today I will even focus on the Coulomb branch. So something very, very simple, but because it is so simple, we can really get into the details. So still in this motivation part, just as a reminder, n = 4 super Yang-Mills has this parameter, which is the complexified gauge coupling. So it contains, it contains the gauge, the Yang-Mills coupling here, and also the theta angle. You can complexify this into tau. And very naively, if you ask what is the space of all n = 4 theories, well, first you have to fix the algebra, so say SU2, and then you can choose those parameters, theta and J Yang-Mills, as you like. However, you know that theta should have periodicity, it's 2π periodic, so tau will have a periodicity of 1. Oops, sorry. And so very naively, the moduli space of such n = 4 theory, this would be this strip in the complex tau plane. I picked this strip because of the theta periodicity. But of course, as you all know, there is S-duality, which is a very non-trivial relation between the theory at a certain coupling and the theory at a kind of inverted coupling. Tau goes to 1/tau. And so the less naive picture is when you quotient by this tau goes to -1/tau, and you keep in mind the fact that there is tau goes to tau + 1, which should also be modded by, then you have the whole SL2Z modular group that appears, and then you have to restrict to a fundamental domain like this. And then this fundamental domain, I mentioned it here, you can compactify this, and it's just a sphere with punctures at which you have cusps or elliptic points. Doesn't really matter too much for this talk, but there is this thing I will call the modular curve when you compactify it. But now, this is the story without taking into account these global structures. So just so that we're clear on what I mean by global structures, again, it's the global form of the gauge group after you have specified the gauge algebra. So I mentioned SU2 and SO3, but just to give an example which is slightly richer, if you take the gauge algebra SU4, then you have 4 groups with that algebra. There is SU4, and then you can mod out by subgroups of the center. So the center is Z4. Z4 has 3 subgroups, the trivial, Z2, and Z4. You can quotient by each of them, and then this gives you 3 global forms. But actually, gauge theories need one more refinement on that, because the periodicity of the theta angle that I said at the beginning, it's a 2 pi periodicity, it actually depends on the global form that you pick. And if you pick, for instance, the SU4 mod Z4, then theta is not 2 pi periodic, but 8 pi. And so you will have 4 different global structures. And so in total, for SU4, you have this diagram, and this was, I think, first pointed out by Haroni, Saibergen, and Tachikawa in this very nice paper that explores all the possible global forms that a gauge theory can have. It's called Reading Between the Lines of Gauge Theories, I think. And the reason is because they obtained this classification by looking at which line operators you can build in your theory. And they show that indeed they are, if you take algebra SU4, you have 7 different options. And they are illustrated here. And in this diagram, I take one more step. I add the T and S generators of SL to Z. So if your theory is actually n equal 4 super-Yang-Mills, then it turns out the different global structures are related by the dualities. So for instance, SU2 is not S-duality invariant. If you apply S-duality, you have to invert tau, but also you move from SU2 to SO3. And similarly here, you move, for instance, from SU4 mod Z4 to SU4 by S. I hope it's visible, yeah, the yellow thing. And well, just I put some color here to show that there is 6 of the 7 structures which are related by dualities, and then there is one which is alone here. And again, how you get there is by looking at line operators. So the goal of this talk will be to recover some kind of story similar to that, relatively close to that, but from a totally different perspective, just from the moduli space of vacua. So, but just so remember, we were there for the space of QFTs, and now when you take into account these global structures, you have to extend, because as I said, I already said that, SU2 at tau goes to SO3 at -1 over tau. The periodicity of theta depends on the global form. And so if you apply this to the SU4 example that I showed before, you see that, for instance, if you start from SU4 over here and you apply S-duality, then you get to SU4 mod Z4 labeled by number 0, which is this region here. And then you apply T and so on, and then you cover exactly 6 regions here, so that these are the 6 global forms. And then there's that one which is on a separate diagram because it's not connected by duality. So in the end, the moduli space of n equal 4 theories with SU4 algebra is actually the union of these 2 things. And these 2 things are modular curves. The one on the right is the modular curve that I talked about at the beginning, the one from SL to Z. But then that one here is a modular curve for some congruent subgroup, which turns out to be gamma 04 in some notation. I will explain what this is later if you don't know. So now this is the goal of this talk. Yeah.
Arithmetry or what kind of?
No, I just picked SU4 because it's the first example in which you have 2 orbits. It's the gauge group, yeah, it's the gauge algebra. SU4 is the gauge algebra. If you want, you can take sorry, oh yeah, there's a typo here. This is Z2, yeah, sorry, there's a typo. So that's the gauge algebra. The only reason I do it for SU4 again is because that's the first time when there is a disconnection like that. Right, so now I want to compare this and to take I will not talk about line operators or anything. I'll do something completely different. Again, my point of view is to look at the moduli space of vacua. And for each, take an n equal 4 super-Yang-Mills theory with a certain Lie algebra, and then ask what is the set of all such theories. So I kind of emphasize that because it's a space of moduli spaces of vacua. We are kind of going one step higher. So let's unpack what I mean here. So we fix the Lie algebra. This will be fixed. say SU4, SU5, whatever, G2, whatever you like. And then in principle, we should also pick a polarization. This is what gives the Dirac pairing, if you want, between the different particles. The most natural thing to do is to pick a principal polarization. So I will not really talk about that anymore in this talk. I will ignore this J. J will be the identity matrix, or rather the standard symplectic, antisymmetric matrix. If you want to know about non-principal polarization, we can discuss afterwards. And now the Coulomb branch for a particular n equal force Super-Yang-Mills theory with a certain gauge coupling is specified by a special Kahler structure. I will review what this is later. It's determined by a number tau, and I call it tau because it will play the same role as the previous tau, but a priori it's not the same, and also some discrete data. And our main result, the thing that I want to explain now, is that in many cases, but not all, and we will see the difference, the space of all special Kahler structures is the same as the conformal manifold seen before. So yeah, that's not really a statement that you often hear, so I just repeat that. This picture here, these are the modular curves. These are the same as the compactified version of that. And what I'm saying is that if you ask me what are all the possible Coulomb branch geometries for n equal 4 Super-Yang-Mills with the algebra SU4, I say these are exactly the same thing. So there's a one-to-one correspondence. So the goal is to explain this and to explain when it differs from the expectation. So this was the motivation. Hopefully this will become clear by the end of the talk. So first of all, I review a bit the vacua of n equal 4. Then I will show how we classify this, and I will show some examples and so on. And maybe if I have time, but I don't know, talk about the mass deformations and connect to that. Okay, so now let's go back to basics and talk a little bit about moduli space of vacua. So I don't think I need to recall to this audience that if you have a 4D n equal 2 theory, well, you can just read from the superconformal algebra, and in particular, so this is here, there was a question about the R symmetry. So here, the R symmetry is that part here, and the R symmetry breaks into two parts, an SU2 and a U1, and then when you have an n equal 2 preserving vacuum, it can be well, some random vacuum, but if some of the factors leave the vacuum invariant, then it will be a Higgs branch or a Coulomb branch vacuum. And then the other ones are mixed branch vacuum. And the geometry of these branches, for Higgs branch, it's a singular hyperkähler variety, while for the Coulomb branch, it's a singular special Kahler variety. So just as a reminder, there are two notions of singularity that we should not confuse. All these spaces are complex. They have a complex structure, and so you could talk about the complex singularities, which are the singularities of the space when you view it as a complex algebraic space. You write equations and you check when it is singular. And then there are also metric singularities, because those spaces are actually real singular manifolds, and there is a metric on them, and then the metric can diverge at some point. The curvature can diverge. And the metric aspects are much more difficult to grasp. So just this is a little table to remember where we are. On the Higgs branch, I said it's a hyperkähler manifold or singular manifold. This is the metric thing. This means that it has a metric, which is hyperkähler. But then the algebraic version is the symplectic singularity that I believe has been mentioned or will be mentioned in this workshop in other places. So, but this is not what I'm interested in today. Today, I want to look at the Coulomb branch. And the Coulomb branch, the reason I emphasize this little table is because the complex structure of the Coulomb branch is very often trivial. It's just C to the R. R is the rank. So what really matters is the special Kahler structure. And so I will need to review what this is. So all this is a very general discussion. But today, we will need the simplest of all examples. For n equal 4 Super-Yang-Mills, it turns out, and here I will review a few well-known facts about the geometry. It turns out that the full moduli space is just a flat orbifold. So take R, the rank of the algebra, W is the Weil group. Then M, the moduli space of all n equal 4 preserving vacua, is just C to the 3R mod W, where W acts on each C to the R factor by just the fundamental reflection representation of the Weyl group. And the picture if you take G equals SUN, then in string theory, you have a very clear picture. You just put N, well, here R plus 1, these 3 branes, and the Weyl group is just the permutation of those branes. And the transverse directions are in R6, which is a C3. So that's how you can see that the moduli space is just this. So, okay, that's simple. And the fact that it is a flat orbifold is, of course, a huge simplification. And this is what allows us to classify those things. Yeah, this is just a slide to refer to a work we did with Julius a few years ago, where we looked at the singularities, metric and algebraic for that. It's simple enough that you can really do it, and you can draw a Hasse diagram that we like to do, but I will not expand too much on this. It's basically just the breaking patterns of SUN. So here I illustrate this. But I just put this slide to say that this is not what we will be doing today. We will not be looking at the Hasse diagram of singularities because we will be looking at the Coulomb branch, which, as I said, has no complex singularity. So let me just skip this. If you want to, we can also discuss this maybe after the talk. So the way we work, how do we have a Coulomb branch emerging? Well, we consider n equal 4 as an n equal 2 theory. We pick, so algebraically, this means picking a n equal 2 subalgebra in the n equal 4 algebra. This amounts to picking a Higgs branch. Then the Higgs branch will have the same singularity patterns as the full moduli space, so the thing that I showed on the previous slide. But the Coulomb branch, as I said, is now freely generated. It's just C to the R. And so now I want to focus on the special Kahler structure, which encodes the metric on the Coulomb branch. OK. So now it becomes a bit technical, and we will not need this technicality. I just needed to include, because I keep talking about special Kahler structure, so I needed to have the definition. So first of all, there is some amount of freedom. Not everyone agrees. I would refer to this, to this paper by Fried in '97 for a nice discussion. Basically, the structure is as follows. You have the Coulomb branch, which is this R-dimensional, like C to the R. And then on top of this, you have some kind of fibration with dimension R. Well, yeah. So if it was one dimension, it would be curved. So this is what I tried to draw here. But in general, it's this dimension R spaces, which are fibered over it. And this is what this definition says. So you have a complex vector bundle over the part of the Coulomb branch, which is like C star. So you have to remove a certain locus. And then there is a group which plays an important role, which is this SP2RZ. So if R is 1, again, this is just SL2Z. So that's the modular group that acts on a torus. But then more generally, it acts on R-dimensional abelian varieties. And this is basically you have this fibration. The abelian variety becomes singular on a certain locus, which is of lower dimension than C. And everywhere else, you have a smooth abelian variety. And then when you turn around this singular loci, you can have some monodromy. That's basically the information that is encoded into this special Kahler structure. No, the fibers are compact. And they are, again, think of abelian variety. A complex tori. Yeah. Well, OK, we can discuss the details of the definition. In the end, what matters is really just these monodromies, these SP2RZ valued monodromies, which encode how the cycles of the compact abelian variety are glued together when you turn around. So again, here, the reason why it will become simple is because of these two additional facts. So the first one is for when you have enough supersymmetry, so more than 3, there is an isotrivial special Kahler geometry. So the fibers are actually all isomorphic. So there is a single abelian variety. It's always the same here. The smooth one is always the same. Yeah, the only thing that happens is that it can degenerate on this singular loci. So because of this, and combining with the third fact, which are the fact that we can restrict to principal polarization, in the end, what we need to do is, so you see the polarization was here, this J in the symplectic group, but now we can restrict to principal. And I said, in any case, that's the assumption I'm taking. So in the end, the special Kahler structure is just specified by the periods of this abelian variety, which are the same everywhere. So this is what I call tau. This is a bold-face tau. It's a matrix. It's an R by R matrix of periods. And there is a representation, S, of the Weil group into sp2r. This representation tells you, again, there is, for each element of the Weil group, there is a fixed locus, and then you have to say how the period matrix changes when you go around. So again, this is a bit technical, but in the end, the only thing we need is that. And so all of this, I summarize with this fact number 4. So an n equal 4 SK structure, when you fix the algebra G, it's an sp2rz orbit, because you cannot pick a particular basis. It has to be an orbit. It's an sp2rz orbit of pairs of S and tau. And S is the monodromy representation. So technically, it's a symplectic integral representation, which is Q equivalent to 2 copies of the fundamental reflection representation. That's basically the fact that you have electric and magnetic components to the symplectic matrix. And then tau is, as I said, is the period matrix, and it has to be fixed by S. And then there's an action on these pairs. Okay, so that's a mouthful definition. In the end, and now is the end of the very technical part on these special Kahler structures. In the end, if there's one thing to remember from all of this, is that the initial problem reduces to an algebraic one. Classify, well, let's forget about tau for a moment. We want to classify these representations. So now again, the algebraic problem is take a Weil group, and then you want to know what are all the possible representations of the Weil group into sp2rz, which have this prescribed form. So you should have an electric and a magnetic part in which they act like the reflection representation. So this is the problem. This is what we classify there. This classification is the same as the classification of the Coulomb. Yes?
Why expect copies of that? What I understand, what comes to that, from the down,
yeah. Yeah, the other one would be, I guess it's because there is, here we use the fact that n equal 4 has S-duality, and so there is a magnetic part which is indistinguishable from the first one. So it's this, but it's the same. So so technically the representation will be again, if you have principal polarization, then it will be just the inverse transpose of the one. Yes, that's where the polarization plays the role. And so in general, the other one might be different. So again, if you want, these are interesting things when you change the polarization, and so we could discuss that. But here for simplicity, that will be the setting. So now, given this, let's classify. So now it becomes just, for all this section, will be just an algebra problem. So just to illustrate what are the kind of problems we might have, let's just look again at our favorite example of SU4. So here the Weil group is S4, the symmetric group. And so that we're all on the same page, the fundamental reflection representation is, well, it's generated by 3 reflections. And you can write the matrices. Like it's really, yeah, you can write down these matrices. W1, W2, W3, and then from the 3 generators, you get the whole group. So these 3 matrices, you can check that they square to the identity, and then they satisfy the correct commutation relations. But here you see I put -4, but then I could actually replace this number by -d, where d is some number that divides 4. But then be careful, if you want this to still be a representation, the -d here, then d should appear on this side. And so you see there is a balance. You have to take d to be a divisor of 4, because otherwise that one here would not be an integer. So just from this example, I'm just telling you here that there are 3 integer representations of S4. I'm not proving here that that's it, but I'm telling you these are exactly the 3 representations of S4. Which means whenever you have a representation of S4, which is equivalent over the real, say, to the fundamental reflection representations, then you can show that over the integers, it will be equivalent to one of those 3, for d equals 1, 2, or 4. Well, fundamental representation is a notion from real or complex. So you can take any of them, d equal 1, 2, 4, even pi or whatever number.
Okay, what's the dimension of that?
3. So yeah, sorry. Fundamental representation is dimension R, the rank of the group.
Okay, so it's the one given by the hook.
Yes. Again, when you have Weil groups are Coxeter groups, so they are defined as reflection groups. So that's the one I mean, the reflection one. Okay, so the strategy will be to do the following. So again, this is an R by R representation, right? It's 3 by 3. We want symplectic ones. So the idea is, how can we build a symplectic one? Well, the most naive idea is, let's put one of those z-valued representations here in the upper corner. And then here, this is the question that Michele asked, what do you put here? If you have a principal polarization, here you have to put the inverse transpose. If you have another polarization, then you put something that I call R check. But okay, let's just say that this is fixed. And then you can try to block diagonalize your thing. So, and we will see that it is possible to indeed have zeros over here. So it's a restriction, but we will see that we can put 0 here. And then you can put maybe something up there. And that would be something which kind of binds electric and magnetic sides. So the representation would not just be a direct sum of the electric and the magnetic one, it would have some binding. So the strategy will be, we will try to find a list, a list of such representations, and then we will try to see how they are connected by dualities, like which ones are actually the same, which one did we overcount. So the point will be that we show that it is enough to consider a representation of that form with a 0 here. And since it is enough, we just need to remove what we overcounted. So we will have a diagram a bit like this, where we have a bunch of representations, and then we realize, oh, actually we had, say we constructed 4, but then actually 3 of them are the same, and 1 of them is alone. And then once we have that, we will be able to read a duality group out of that. And from this duality group that I called gamma here, we can construct the modular curves, and then we will get, at the end, the moduli space, the space of all the possible Coulomb branches. So that's how we will get to that picture. So let's do this in more detail now. So the first step, so again, we will really follow the steps that I illustrated here. So the first step is find all Z equivalence classes of representations, which are Q or R equivalent to the reflection one. So again, for SU4, there were 3. And it turns out this has been done actually not so long ago in 98 by a fight. And well, the list is given here. So it's kind of what you would expect. Basically, you can construct all of them by, so okay, yeah, first of all, I need to recall this basic fact that an integer valued representation is the same as a lattice representation, because then the change of bases are just integer matrices. And so you need to find nice lattices on which the Weil groups act. And well, the natural ones are the root lattice, the weight lattice, and some other lattices in between. And so this table here tells you that indeed that's all there is. So when you have the non-simply laced algebras, you need to take root and co-root, and otherwise you take root, and then, well, okay, so that's the number of lattices for each. That's the number of lattices for each algebra. This sigma 0 here is the number of divisors. So you see there is one little weird thing here that maybe, I mean, it's completely normal, but for A, for SUN or AL, it's the number of divisors, except for A1, because for A1, all the lattices are the same. So this is it's an accident, probably because for A1, this is the only abelian Weil group, it's Z2. And so for Z2, you cannot really represent it, the reflection representation is one-dimensional, and there is just one. We will see that this fact will be important. But okay, otherwise, these are just some lattices which represent the Weil group. Now, once we have this, as I said, we want to find canonical forms for these representations. So how do? We start from an integer representation from the list in the previous slide. I call this A. And then I put it up there. This is my RA. Then here in the bottom right corner, I put the inverse transpose of that. And then I'm trying to find representations where there is a 0 over here. So the last thing that we need is to fill in what is in this corner here. And it turns out, if you work out the algebra and impose that this is indeed a symplectic representation, you find that the condition is that this thing that you put here is not a representation of W because it sits in the upper right corner, but it's what's called a binding. So a binding is defined by some symmetric matrix D, and then you just construct this L as R times D minus D times R inverse transpose, and then you can check that if you put this definition in here, then it is indeed a symplectic integral representation, provided this L, of course, has only integer coefficients. And so this is a nice class of representations, but then there is this theorem that goes back to, I don't know actually who is the originator, but there is this textbook by Curtis in the 60s, which proves that indeed any representation that satisfies the conditions I asked at the very beginning can be put in this form by some conjugation. So you can do some kind of Gaussian elimination and have a 0 here, and then L has to have this form. So what this is telling you is that in the process of classifying all the representations, it will be enough to look at those ones, because we know that everyone is connected to that by some basis change. So now we want to classify all the possible things that we can put here. And the thing we can put here, as I said, is defined by this symmetric matrix D. So now, what are these matrices that you can put? What are these bindings, the thing that bind the electric and magnetic side? Well, now this is the most technical part of the thing. Well, I'm just saying it here. These bindings, to the group of bindings again, a binding is a map L, as in the previous slide, such that there exists D, which is a symmetric matrix with rational coefficients, which satisfy the definition I gave above. But then there is a subgroup of inner bindings. The inner bindings are those for which the D matrix has integer coefficients. And it turns out that if you want to find all Z equivalence classes, you need to compute the quotient of those two groups. This is the binding group. And you can also phrase it as some X group from representations. So that's a technical computation. The way we did it is we have a Mathematica code that computes all of these things, and there are nice algorithms based on Smith normal forms and so on, which can do this for you. So you don't need to worry about that. And then in the end, it gives you the full list, and it's a finite list of Ds that you need to put up here. So to summarize, remember, we have a finite number of choices for A. And now for each A, we have a finite number of choices for D. So in the end, we have a finite list of representations that we are certain cover all possible classes. So this finite set, I call this by this letter. It's not a J, it's an I. It's a matrifrac I. So it's the disjoint union of all these X. It's just that this set of representations which are enough to cover everything. And the last step is to know, now I know that I have enough, but I have to remove if I have too much. So I have to compute which of them are dual to each other. And then there is this very nice mathematical structure that for each pair of elements of this set, we can construct the intertwiners, which are just some matrices valued in SP2RZ. But the nice thing is that they are actually parametrized by SL2R. So let's unpack this. So for each pair of indices AB, these are two different representations. I can find an M such that M AB times SB is the same as SA times M AB. And that's true for every gamma in SL2R. So you have something which is parametrized by SL2R. And in addition, this parameterization is the right one because you have this composition law. If you take MAB of gamma, MBC of gamma prime, it's MAC of gamma gamma prime. So this is an extremely nice and constrained structure, which tells you everything about dualities. And in particular, if you want to find what is the duality group of a particular structure, you just look for which gammas give you an integer matrix. So you take SP2RZ, and you look at which gammas give you this. That's S, that's the duality group. And then, of course, two structures are the same if this set is non-empty. It is non-empty, then it means that there is some map such that the intertwiner here is integer valued, so then they will be in the same Z class. Okay, and that's the end. So the point is we know which ones are equivalent, and we know the duality group. These are just the SAA. So maybe this is a bit abstract, so let's illustrate on our favorite example of SU4. So again, I already mentioned that there are 3 Z representations of S4. These are exactly the same metric. The only thing that changes is the number here, 4, 2, 1, and then here 1, 2, and 4. So this is our basic starting point. We have 3 of them. This is step 1. These basically correspond to the 3 subgroups of Z4. Then step 2 and 3 is we have to find all these bindings. So then this is where we need the computation, as I said, using Smith form and so on. Yeah, maybe maybe I skip some of the details here. The point is you can compute this. It's some integer algebra, so it's not always easy, but it can be done. And then what you find is that the forms of the matrix D is very constrained. It's parameterized by some integers and some real or rational number. And then from there, you can see, and let me just explain this because this is the subtle part. If I go back to the definition, if you have a binding L, it's an integer binding if there exists a D with integer coefficients that make the definition work. So we need to find, since this is the most general form for D, you have to look for every integer n1 and n2 and n3, can I find a beta that makes this matrix integer? And here you can see that you can. So for instance, if you take n1, n2, and n3 so that this number is odd, then you would have a half integer. But then you can pick beta to be an integer, a half integer as well, and then this would be integer, and then everything else, you see, it has a, well, okay, no, here it has an odd coefficient, but then you can, well, I mean, you can work out the fact that yes, for every n1, n2, n3 in integers, you can find a beta such that this is integer, and that tells you that the x vanishes. But then if you take another representation, the coefficient changes a little bit, and then you cannot do that, and you find that there is a Z2 group. So again, if you want to see how we do this in an algorithmic way, you can come to us. In the end, the result is that there are 4 equivalence classes. The 1, 2, and 4 now get decorated with the X group, which is trivial for 1, trivial for 4, but for 2, it has 2 elements. It's a Z2. So this set, this capital I that I had, has 4 elements. You have 4 representations. You know that every representation is equivalent to one of these 4. But now we want to know, are there some which are equivalent to each other? And then for this, we need to compute these intertwiners, this M structure. And let me just show it. So this is the output of the, so I don't know if it's readable. Yeah, this is the output of the Mathematica code. So this is an extremely nice structure. You see, each matrix is parameterized by ABCD, which is an SL2R matrix. These matrices, you can multiply them in all possible ways, and they will, if you multiply, I don't know, this one with this one, it will give you this one, and so on. And then you have these integrality properties. And if you look carefully, you see, for instance, that here, for this matrix to be integer valued, you need this C to be even, to be a multiple of 4, because there is a 4 in the denominator here. So then the duality group here will be gamma 0, 4. If you look at this one, the duality group will be just SL2Z. This is always integer. And here it will be gamma 0, 4 as well in a disguise, and here as well. So, and also you can look for these other matrices, and whenever you find an entrance ABCD with determinant 1, such that this is integer, then it means that the 2 forms are. So by doing all of this, we reach the conclusion that actually out of these 4 representations, 3 of them are the same, and 1 is on its own. And the 3 have gamma 0, 4 duality group, while the other one has gamma 1. So actually, the picture that I showed at the beginning was the result. This is exactly what you get. We got 4 representations, but actually 3 of them are the same, and they have duality group gamma 0, 4. The other one is by itself. So this is a bit surprising. If you remember what we said at the beginning about the global forms, this was exactly the conformal manifold for n equal 4 theories with SU4 algebra. This was gamma 0, 4 and gamma and well, SL2Z. So the space of Coulomb branches is the same as the conformal manifold for SU4. So now, as I said, because this is the special, we are classifying the special Kahler structures, which encode the geometry of the Coulomb branch. So we are looking at the space of all possible geometries on the Coulomb branch. How many branches? Well, there's the Higgs branch. Well, here we are doing n equal 4 super-Young mill. So in principle, there's not even a branch. But we selected an n equal 2 subalgebra. And then we have the Higgs branch, the Coulomb branch. And now I'm just looking at the special Kahler structure on the Coulomb branch. Yeah.
Whatever value of the UV coupling, there is a corresponding to branch.
Yes, exactly. But there are several. So the value of the UV coupling, gives now, in order to give the special Kahler structure, you need to give the whole matrix. And the point is you will have various choices, one for each global structure. And there is really a one-to-one match here.
How do you extend the results from the Coulomb branch to the whole modular space?
I'm not really extending it. So before you arrived, I showed the Hasse diagram for the full moduli space. But here, I'm focusing on the Coulomb branch and then on the metric aspects, the special Kahler structure, because algebraically it's just trivial.
So it just extends, right? Like you have 3 coordinates instead of 1 coordinate, it's fine.
Yeah.
The structure exists everywhere because everywhere you have a Coulomb phase. That's the important thing. We have U1 to the R, and that's what's going on. So it extends in the natural way. There is no Higgs branch.
Yeah. Okay, so, but okay. Yes, it's a bit of an artificial naming here anyway. All of this, of course, is rotated by the R symmetry. So as I said, all of this is, it sounds a bit complicated the first time. Took us. Okay. Okay. But okay, now we have a good handle on this algorithm with many subtleties. So here, on purpose, I illustrated with SUN, which is very nice. But then, as you can imagine, things become a bit algebras. But okay, so that's the output. Okay, maybe I should remove that. That's the output. So for each algebra, we can do the same program. And we have the list of all representations that we can construct. And then we group them by equivalence class. So there is one per line. So each line corresponds. Let's see if I keep it in my hand. Right. So for each of them, we can compute compute the duality groups and so on, and much more data, but let's focus on that, because this is the thing that we want to compare with the space of global forms at the end. And so we use the color code. Each time the entry is in black, it means that there is perfect agreement with the global forms, which is very surprising. Like, this computation is, first of all, completely independent, and it doesn't even compute the same thing. It computes something different, which, yes, it is related. You can argue that the index of the duality group gives a lower bound on the number of global structures, because if you have an equivalence in the UV, if the things are the same, are related by S-duality, then clearly they should have the same moduli space. But you don't expect this to be necessarily a very fine invariant. Maybe by just looking at the Coulomb branch, you would forget most of the structure. But actually, you don't. You forget only in the cases where it's a red entry. And you see at the very top here, there is this red thing. So it's quite bad to have a story that works almost everywhere, but not for SU2. But okay, that's life. And this is related to this fact that I mentioned at the very beginning, that the value for SU2 is so small that this program kind of gives nothing. So it cannot distinguish between SU2 and SO3. But for any other SU, it can. And for basically everything, it can see, but not for SU2. Also, there is for BC2, there is a slight problem. But, so basically, when the group is too small, it cannot completely see it. And we don't really understand a deep reason why. And in particular, it's a bit unclear why the special Kahler structures on the SU2 Coulomb branches are so unconstrained. I mean, this is the result of the computation, but is there a fundamental reason? It's not completely clear. And then I would like to point out also some nice other aspects. So for instance, here in the D even, so the first case where this happens is for D6, which is SO12. So in SO12, you have a weird duality group here that we called delta. This is the only one which is not a congruence subgroup. So congruence subgroup is a subgroup of SL2Z, which is defined by some congruence. And that one is not one of those. And indeed, it could not be because it has index 2 in SL2Z. And no congruence group has index 2 in SL2Z. But it nicely fits with the results of reading between the lines of Aharoni, Saibek, Tachikawa, that indeed, if you look there, for D2R plus 2, there is an orbit of just 2 global structures which are exchanged. And actually, this is one of the points which also triggered this, this whole project, that we were wondering, like, for each of the global forms, we can identify some congruence group that permutes them. But then for that one, it's not possible because it's 2. And indeed, the analysis here shows that this group, this non-congruent subgroup appears. So everything turns out to be very, very close to the connection with global structures. However, again, some discrepancies in red. And also in blue, I don't want to talk about this too much, but in blue, there are the effect of outer automorphisms, which are very subtle, in particular when joined with non-simply laced. So you have some Hecke groups that appear as well. Okay, so that's the end of this computation. Again, an independent computation of something which should not, in principle, be so close to the global form, but it turns out to be very close. And now I want to point out some other mysteries. I have 10 minutes, right? A bit more. 15 minutes, okay. Good, so I have time to talk a bit about the mass deformation. So so here I point out some mysteries, but there will be more when you try to look at another observable, some other thing that you can say from the IR, from the vacuum structure about S-duality in particular. So this thing is what happens upon mass deformation. So you take your n=4 theory, and then you do the most vanilla thing that you can think of. You give mass to, if you want to preserve n=2, you give mass to one of the hypers. You see it as n=2, and then there's a hypermultiplet in the adjoint, and then you give a mass to this. And then if you want to break to n=1, then you give also a mass to the remaining chiral multiplet. So that's what is called n=2 star or 1 star theory. And then, now that you have broken supersymmetry, the nice thing is that the moduli space of vacua, well, maybe it's not nice, but it becomes much, much smaller. And in particular, the gapped vacua will be finite in number. Now, the question that we wanted to ask is this information, this number, now it's just an integer, how many vacua, is this sensitive to the global structure? And as you might expect, if you just leave your theory on R4, then no, it doesn't feel the difference of global structure. But then, if you want to feel it, you need to put some non-trivial topology. And one way of doing it is just to put the theory on a circle. So if you put it on R3 times S1, then there will be a difference. And now that's just a number. It's not a crazy SP2R representation thing. It's just a number. So let's look at this number. Again, the simplest case is SUN. And for SUN, the number of gapped vacua on R4 is just the sum of the divisors of n. Basically, this follows from a semi-classical analysis. You look at how the group can be broken to pure n=1 theory, and then you use the known results about the Witten index of pure n=1 theories. And then it's easy to see that for each divisor of n, you can break to the theory to a theory with pure n SUN over d, and that thing has, SUD, and then that thing has d vacua. And so the total number of vacua is the sum of divisors of n. Now, if you put the theory in a circle, what changes is that now you have all these lines in these theories, and the lines can wrap the circle, but then if the circle becomes small, this can have a non-trivial vev, and then it will change the number of vacua. You will have some of the vacua here will be duplicated or have multiplicity. And if you do this carefully, so if you take the SUN mod ZM, so M is a divisor of N, and then you take the nth version of that, then the number of vacua is larger. This is what I just explained. And then you can find that the number is given by this formula. That was actually my first introduction to this whole topic, and it is almost 10 years ago already with Jan Trost. And the nice thing is that this formula, as it should be, is modular invariant because S-duality is an exact equivalent. So if you take SU4 and SU4 mod Z4, of course, they should give the same result. And then you can check that this formula is indeed invariant. However, if you take SU4 mod Z2 with n equals 0, you can see that this number is different. So if I take all the 7 structures for SU4, for 6 of them, this number gives 12. And for one of them, the one which is alone, it gives 16. So that's really I mean, if we needed another argument, that's another argument why the theories are really different. And they cannot be related by any duality because the number of vacua is different. So this is what I say here. It's modular invariant. It's actually a nice exercise to prove that. Not so easy. But then it proved that this is constant within orbits. Yes. It involves the psi Dedekind function. I didn't put it here, but yeah. Yeah, it's not phi. It's I don't know how it's called, but yeah, but there is a form I can show you if you want. I mean, sorry, sorry. Let me correct this. The number of orbits. It's just the number of square divisors of n for SUN. Now, if you want the total number of vacua, it is this thing that I said with the psi.
You said 7.
No.
7,
No. 7 is the number of vacua on. Sorry, no, there is no 7. This number is 7. Yeah, the number of vacua of SU4 on R4 is 7. The number of vacua on. Okay, let me write it here. So if you have G equal SU4, then the number of vacua on R4 is 7, which is 4 plus 3 plus 2 plus 1. And then the number of vacua on R3 times S1 is 12 for SU4 and all the forms connected to that, and 16 for SU4 mod Z2 number 0. This is what I'm saying. This is what this formula gives. And so yeah, it's constant on orbits. Okay, so how? So again, as I said, we can prove this using a semi-classical analysis, looking at how the group breaks and so on. But there is a nicer way, well, maybe not nicer, but another way of finding it, which is closely connected to the Coulomb branch geometry that I talked about. And this takes a detour through the correspondence between n equal 2 for the theories and integrable systems. So the link should be, but again, this is a bit of a mystery, the integrable system which is associated to the n equal 2 star theory, compact divided on S1. So that integrable system is an elliptic Calogero-Moser system. So for SUN, what this system is just you take a torus, you take a 2 torus, and then you put a bunch of particles on it, so n of them for SUN, so here 4, and then you ask these particles, they interact with a potential pairwise interaction given by this elliptic Weierstrass function. Sorry, here. So there is a elliptic function defined on the torus, and then you put pairwise interaction, and then you ask, and that's the statement of the Nagy-Witten observation, that the vacua, the gapped vacua on R3 times S1 should be in one-to-one correspondence with the equilibria, isolated equilibria of the integrable system. So you need to find how to put these particles that interact with the Weierstrass form, how they can form, how they can be stable. The problem is, where does the global structure enter? And the point of this other paper that I mentioned at the beginning is that you have to be very careful about what are the periodicities that you use when you define this integrable system. What happens if a particle goes around? Does it go on a different sheet and so on? And to illustrate this, so first of all, instead of drawing a torus like this, we can draw it as a rectangle, and we put the particles like this. And then we can look for all possible vacua in this way. And then we can really find this one-to-one correspondence between these equilibria and the vacua given by the formula on the previous slide. And so if we do it for SU4, this would be really a very, very complicated story, because for each global form, we have 12. So we will have 6 times 12 plus 16 a number of vacua. So that's a huge number. So we still did it for SU3, which is a bit lower. And so that's this duality graph here, which probably is not really readable. But every entry here, there is a copy of this torus, and then the points denote where are these particles. And then you can act with modular invariance on these configurations. And as you can see, they map the global structures between them. So here, for instance, you have 1, 2, 3, 4, 5, 6 vacua for the SU3 theory. And here you have the 6 vacua for the PSU3 index 0, the 6 for the PSU3 index 2, the 6 for the PSU3. Of course, there is only one orbit for SU3, so it's always the same number, 6. And then they are connected in this way. So that we see a bit better, let me just show it for SU2. So again, the trick is just that we change the periodicities. So we have to consider, for instance, for SU2, we have to consider the periodicities in such a way that, for instance, there is one vacuum in which there is only particles which are aligned on the vertical axis. And for SU2, there is no additional freedom in this horizontal direction. But then for SO3, you can move one particle here in the middle, because you kind of take a double cover of the torus. So here I decided to not put the formal definition of all these change of periodicities, because again, it's a bit technical, but hopefully the illustration here shows that for each global structure, SU2, SO3 plus, SO3 minus, there is one of the R4 vacua which duplicates. And so that's how you go from 3. So here for SU2, this would be 3, and this would be 4, this number. And you go from 3 to 4 because one vacuum duplicates. But then here is another conundrum, that here the SU2 analysis really works. And so from this analysis of the vacua, you do find the 3 global forms and so on. And so even though in principle there is a connection between the special Kahler structure and the integrable system, this is something that I don't understand. How come we get the correct result for SU2 here, but the SK structure doesn't see it? So, okay, I will leave this open. And then just point out that there are many, many more complications there. Because whenever you move outside of the A algebra, so something other than SUN, then these vacua of the elliptic Calogero-Moser system become extremely complicated to understand. And even there is some kind of spontaneous breaking of modular invariance. And okay, I have 1 minute. So for instance, for okay, I'm okay. So I just want to point this out because it's something that has. So this is a picture from my first paper, and I still don't understand 10 years later. So what happens for SO8? This is the first example, which is really different from SUN, is that there is a critical point in the middle of the fundamental domain. You see here at a particular value of tau, which is about 2.41 I. So this is the critical value for SO8. This is the exact formula if you want it. And there is some kind of instability that arrives there. And because of that, in the IR, modular invariance is broken. So what I mean there is, if you consider that the T generator is moving around the cusp of the modular curve, so up there, and S is moving around the I point here, then you know that in modular group, you have that ST to the 3rd power is the identity. This should act trivially. But here, because of this point that appears here in in the middle of the fundamental domain, you can no longer derive this relation. The way to derive this usually is by deforming the contour from there to the top, and so that you get something empty. Here you cannot do it. So here this relation no longer holds. So this is very, very surprising. And because of that, we cannot really make the analysis, the connection between this and the special Kahler structures work after you have this mass deformation. So these are more questions. Again, this last part is full of open questions. It's more because this is a workshop, so I hope that this triggers ideas. So I wanted to put all my non-understanding of things at the end. So that's how far it goes. Let me just conclude that we have introduced a new method that classifies all the SK structures. That's the solid part. We have this table of results, and now I have to point out that this can be applied much further than n equal 4. Actually, to tell you a bit about the story of this project, initially we were interested in global forms of n equal 4, n equals 3, SCFTs. And then we realized we should classify the SK structure. So let's do just a small exercise. Let's do it for n equal 4. It must be well known and should be easy. So that was back in 2021. So 4 years later, we're still, now we are basically there. But okay, now hopefully we can go further soon. We find these surprising links with the duality groups. But again, I cannot say full agreement. First of all, because we don't expect full agreement, but we were expecting either to have full agreement or complete disagreement. And we find almost exact agreement. So yeah, this is a bit mysterious at the moment. And of course, we have relied on very strong assumption that so much supersymmetry gives that we have these flat orbitals with isotrivial structure. Many questions arise of what to do when you don't have these assumptions. And then there is all the questions that I put in the previous slides that are also open. And I'm very interested in if you have any idea on what could happen here or here, let me know. So thank you for your thank you for your attention.
Question for Antoine?
Do we understand your talk in the context of Guyotto curve and Simon-Witten curve, especially, for example, like n equal to star?
Yeah, that's a good that's a good question. Right. So the Guyotto curve would always be just a torus. And then indeed, probably the Simon-Witten curve would be a cover, which might be this picture here for SUN. We're close to this picture here. But since we have several pictures which look the same, we would need to go into the details and see, for instance, take SO8. And I don't know on the top of my head how it works exactly. But yeah, there should be some connection. Maybe that's another direction to explore to try to understand the whole pattern.
Along of the third line of the yeah, that one for Gauss press, say glasses at least.
Yeah, so yeah, that's another good question. So the answer is no. Very surprising. Actually, even this line, I think it's not. So in this line you can do. Actually, we did it also with Jan in the past. There is a semi-classical analysis. The number, well, I guess, yeah, you can find the number. If you're just interested in the number, yes, you can do this. And you have to list nilpotent orbits. And then for each nilpotent orbit, you have to look carefully at some properties of the centralizer, of the SL2Z triple, and so on. So yes, you can do that. Then if you want to know the full duality graph, then that's a much, much harder story, because we conjecture that for any algebra outside of SUN and SO5, any other will have these effects like that. And the problem there is that I don't know of a method other than actually finding numerically the stable points of the integrable system on the computer. It's quite hard. So this is what we did with Jan 10 years ago. And now actually we are with the Belgian team of Ricardo and Romain and Valdo. We actually have an unpublished result for SO10, so the same happens. But we don't know, I mean, it's extremely tedious when you increase the rank. So the general story is not known. Yeah. Yeah. And there is actually a method that we developed with Jan long ago, which relies on yeah, how do we know this exact value, for instance? There is a story of the value of the superpotential in each of these vacuum. The value of this should be a modular form. But actually, this would be the case, and this is the case in SUN. This is what Donaghy-Witten did. And then they say, there is a line in the paper that says, it's a straightforward thing to do it for other algebras. Well, actually, it completely fails for any other algebra than SUN. What you get is not modular forms because of these things. So you get, you get extensions of modular forms, and which includes branch cuts and so on. And there is a Galois story that you can find about these extensions. And then understanding this Galois group, this is what gives the exact values of stuff like this. But then it's still heavy to do it numerically, because at some point you need to find a semi-classical datum to fix a polynomial, and then once you have this polynomial, you can run the Galois thing, and then you can know everything. So that's the way we did it for SO10. We didn't just find all the, because it becomes impossible.
Any other beyond S5, let's say, of intervals?
So yeah, so we have the analytic extrema for all the SUN, for SO5, for SO8, this is the one here, and now for SO10. And that's it. Or also for G2. I'm interested in G2.
Take Antoine again.